Hello, my name is Alan Leonard, and I'm recording this for Assignment 5 in Comp 4320, Introduction to Networks. Same thing we've been over throughout all the rest of them. For question 1, explain the primary motivations between IP version 6 instead of IP version 4. The main reason for this is it improves the efficiency, like bandwidth, like traffic, all that, going across everything much faster and better. And another huge thing is the amount of addresses. It's just there's 128 bits in the IP versus 32 bits, which is just exponentially so much larger. And comparatively, that just means not having to change out IP addresses as often because there's so many more that are just open, and especially for the continued expansion of like network uses for phones, consoles, computers, personal computers, everything else, work computers, etc., etc., etc. We're needing more and more out networks and IPs, and this just helps with the new format of how exponential data growth is going across the country and the world in general. So, discuss two major transition strategies between them. Describe the key difference between the key difference is that difference in like the bits. Besides that, IPv6 is much more efficiently formatted for headers, contains less, helps things transfer across and be read much easier. It also allows for packet flow identification in the header itself. Tunneling and dual stacking, though, are two ways transition strategies for going from IP version 4 to IP version 6. Dual stacking involves creating machines that are able to read and translate both. So that way, if an older computer system is using IP version 4, it can still be translated when it gets to the computer or whatever is using IP version 6. And also, IP version 6 can easily just translate to each other. And then another one was tunneling, and that was compressing IP version 6 information in the packets for IP version 4, so that way information's compressed into it, transferred, and then uncompressed when it gets to a thing that uses IP version 6, so it'll be much quicker use across those ones, but still be able to be read across IP version 4, so it wouldn't be uncompressed and translated in the IP version 4s. Link state versus distance vector routing algorithms. Distance vector used shared information across their neighbors, so like one bud would be sharing its tables and connections across with its neighbors, while link state has a complete map of everything across it. And the main differences is that distance uses this information, has a much less traffic, and less likely to spread problems quickly across it, has to go neighbor to neighbor instead of going like everything directly to it. And the problem with that, though, is it also is very able to have loops across those neighbors. So it goes here, and it goes from A to B, B to C, and then decides, oh, C can go back to A, and that creates a loop between it. Also creates infinite steps because you can just keep looping. Link states, though, on the other hand, have a complete map of everything, can't have those loops, can't have those infinite states, but the difference there being is that they can have a lot more information, huge amounts of traffic, and need more bandwidth in general. But they used Dijkstra's algorithm for this link state, and that's very useful for the routing environment and everything because of how when a new change is made, it easily just copies everything across the map and just adds a new part in, finds the newest route across it, much more efficient and time saving, and across those. It's much better for larger scale networks, though. When talking about scalability issues, is because it has a control and process and view of everything, while distance vector kind of loses its ability once it goes to larger and larger, because then it gets more and more chances of infinite states and even more information that they constantly have to translate across each other for their tables. For number 3, traditional versus SDN. Main difference between SDN and traditional is how the maps are sorted. SDN has a centralized control that uses all the networks and routers and everything, while traditional, each router does its own like traffic through its network. SDN also uses open flow, which allows many switches and changes across like everything, and goes in part with SDN being able to control everything at once. Great for allows flow table, math action rule n, SDN controllers to be accessed through all of this, like everything on this separate field that connects everything. and is great for large-scale systems because of how many changes can be made across everything, easily implemented and just changed without having to use specialized hardware or adding in huge entire new parts of the networks. Number two, found differences between intra and inter. The main difference is inter routing is done inside of one single system sometimes, but it's usually between like this system to this other one, or domain-wise, like going across them. While intra is always on the inside between them. Intra uses RIP and OSPF in order to be fast and more efficient across its own system, because it doesn't have to go through all the different things it needs. While inter uses BGP, which is a system of creating special gates to connect across each other. This has two larger gates on the outside, on the outskirts, with all the smaller connection networks between them inside the networks. The hot potato routing network, first part is explain what BGP uses E and I. The external BGP is how the external parts connect to the other systems, and they basically translate themselves to each other in order to get the correct policy across it. While inter are all the smaller gates on the inside of the network that just allow it to work together consistently and reliably. BGP's attributes help it effectively create paths across their networks using the autonomous system paths and use the shortest paths chosen. They use local preferencing to choose one path over another, being like, we've used this path before, we know it works, it's more efficient, etc. Keep to it, and also uses hops to specify IP addresses and which ones should be used. How does BGP policies control routing decisions? Use consistent routings using relationships from the customer's service, etc., like providers and peers. And they have these set up and they know they work, so they try to stick with those ones without having to complicate things. And if those ones aren't available because of traffic or whatever, they go on to their peers' ones and so on. That's where hot potato routing comes in, where hot potato routing just kind of tries to be as fast as it can be, doesn't have to be the most effective, but it does it to limit traffic that's happening. How it does this is like a hot potato, like in the game, just finds the first connection it has, just throws it and keeps going. Route to route. It doesn't matter if it's the most effective, it's trying to be the fastest to get to the destination using all the different routes it has. This allows traffic to move much more quickly, and but a way to limit routing would be to prioritize customer service routing, try to stay away from peers, getting new traffic altogether in the communities created. So we try to limit it down to just what they know, be consistent and not entirely new things to be complicate everything. Analyze the trade-offs between scalability, performance, and policy control in routing protocols. So I found scalability usually changes with the speed. Like as things get bigger, it slows things down because it has to go farther and farther, and keeping all these policies and everything across different networks and domains. With the performance increasing, it changes the flexibility and like general like optimization, because it's just like now it's wanting to just be able to go well. So the adding new things and additions and everything becomes much harder because it wants to stick with what it's got and increase that like the best way they can do it instead of complicating things even further. And that also goes on to policy control, which hurts optimization all around, because it just adding new policies complicates things, makes things even faster and even harder. I say even faster, even slower, and making it even harder. And generally, all usually kind of like work together, like in how they're slowing and affecting things. But yeah, and number 3, I posted a picture of my work and everything, and found the most efficient ways to get across the algorithm. Thank you.